on your self-evaluation. Guys, and what I want you to realize, I know I can only give you so much time, right? I think the self-evaluation is a great thing because it gives you an opportunity to, like I said, address your mistakes, which is one of the best ways to learn, right? We don't know what we're doing or where we're going wrong until we actually try it. It's like throwing a baseball for the first time, throwing a football for the first time, riding a bike for the first time, right? It looks easy on the outside, but if you know, if I turn too sharp on my bike, I'm going to fall down. Okay, so how do we correct that? We don't turn that sharp. And I know I can only give you 20 minutes, but I give you that time as a start. A word to the wise is if you don't finish it, the self-evaluation is the first thing that you should work on. Okay? Because if, like I've said before, I grade on Tuesdays and Thursdays. Okay, and I try to be very up to date, and I honestly cause myself problems when it comes to actually having assignments marked missing that shouldn't be missing. But it's just so that I can reflect your grade as accurately as I have it. So if I don't have what's been assigned and what's due, like your lecture notes and your self-evaluation going into tomorrow, I mark those missing because then it gives you Infinite Campus also telling you, hey, this is missing, but then you turn it back in and I give you full credit as long as you give good effort. So as long as I have it by Tuesday, you're good. And then you think about when your homework's due. Your homework's not due until tomorrow night at midnight. So that gives you all of the afternoon after you finish your self eval. It gives you all of tomorrow if you have any free time to knock it out. And then that homework assignment doesn't hit the grade book until Thursday, right? So I don't know if it's just looking at some of them, we're missing points on the self evaluation because it doesn't seem like we're giving it the effort that it needs, okay, to really correct our mistakes. But I don't know if that's as a result of you think you're under a time crunch that it has to be within this 20 minutes, which that's just not true. It's going to be, you're able to extend that into Tuesday. And as long as I have it by Tuesday, you're good. And worst comes to worst, if I don't have it on Tuesday, I hit the missing sign. You submit it on Wednesday, it hits the grade book on Thursday. Because, like I said, I try to keep my grade book as up to date as possible. So that also goes for your mastery check. That was over the weekend. Lecture ran a little bit long, and I didn't get to remind you to do it. So hopefully you guys knock that out. That will also hit the grade book tomorrow. But for now, we are on to the lecture. Okay, and like I said, today what we're going to be talking about is operations with functions, composition, and composition of functions. So more or less, we're going to be given an f of x and a g of x, and we're going to be told, hey, we want to add those together. We want to subtract those. We want to plug g of x into f of x, which is the composition of functions. So it's very algebraic in nature. It has a lot of handwriting, a lot of work to it, but it's not very difficult as long as we can stick to PEMDAS and we're good at plugging in variables. But it's a lot of algebra. But for first, we're going to go over our 5-minute check. So first one, it says use a graph of y equals x squared to describe the graph of the related function, which is equal to 0.5 x squared. And I'm not going to graph these because I want you to be able to see that we can recognize these changes just from the equation. Okay, so x squared has a 1 out front here, and now we have a 0.5. So this is an outside multiplication of an a value that is between 0 and 1. Okay, since it's outside, that corresponds to vertically. Okay, if it was inside, it would be horizontally, like x minus 0.05 x minus 0, I guess on the inside is how you would say that. But since it's just written as this, we can treat this as our a value. Since our a value is between 0 and 1, that's going to compress our graph down. So this graph should be parent graph is compressed vertically by a factor of 0.5. Okay, and we can get a lot of these transformations just from looking at the equations. Okay, if we go on to number 2, it says use a graph of x squared to describe the graph of the related function y equals x minus 4 squared minus 3. So here we have inside and outside subtraction. This inside corresponds to our horizontal shift, So since it's a negative, this is shifted 4 to the right. This outside minus 3 corresponds to a vertical shift. And since it's a minus, it's going to go down. So this graph has been translated right 3 units and down, translated right 4 units and down 3 units. So that corresponds to answer D. Okay, and remember what I was talking in lecture, I like to think about my horizontal translations as what makes this 0. Okay, a 4 makes that 0. So that tells me, hey, my x value 4 is where the origin or the extremal point used to be. Okay, the next one. Here we have a piecewise function. Once again, this piecewise, it's just graphing these equations for this domain. So we're x minus 3 if x is less than 0. So we're looking for a y-intercept of negative 3. Okay, so graph A's got 1, graph C's got 1, graph D doesn't, okay, with this line, so D can't be it, and graph B does. So we're working A, C, and B, but we can also eliminate one of these graphs because we need to have an open circle on 0. So we can eliminate B because it has a closed circle right here, and we can eliminate D because it doesn't have that x-intercept or y-intercept at negative 3. Okay, so now we're x squared if x is between 0 and 2, and we're looking for a closed circle on 0 and an open circle on 2. So closed circle, okay, open circle for A, that passes. C, closed circle, open circle, that passes. Okay, and then the third part, f of x is equal to 5 if x is greater than or equal to 2. So if we look, A has a closed circle on 2 and it's flat line, so that checks out. But C, we pick up at the x value of 4, so we've eliminated the domain between 2 and 4 here, which is not what the question tells us to do. So we can say conclusively that this is letter A. Okay, and then final one, identify the parent function f of x if g of x is equal to the square root of x minus 4, and describe how the graphs of g of x and f of x are related. So parent function, it's a square root, so f of x should be the square root of x. So that leaves us with C and D here. And then it is a horizontal translation. Since it's a minus on the inside, that means it's going to the right. Okay, so this corresponds to answer C. So when it comes, I know they say graph each one, and it helps to graph, especially if you're struggling seeing what the actual graph does. But you can get most of the information just straight from the equation, because the equation tells you what to graph. So if you're good on where your spots are and what they do, you can fly through these translations pretty quickly. If you're struggling with them, I recommend graphing every one. Make sure you're graphing it. There's no harm, no foul when you graph it. I know like the SAT test is timed, so we don't want to waste time if we can avoid it because time is precious. All right. So we evaluated function. This was lesson 1.1. More or less, what it means to evaluate functions is we're given function notation. So our f of x, and we plug in whatever is in the parentheses. Okay, we plug in whatever is within the parentheses. That's how you evaluate functions. Now we're going to perform operations with functions. Once again, we're going to add them. We're going to subtract them. We're going to multiply them. We're going to divide them. Okay, and division is pretty easy. Multiplication is all about FOIL. If it's binomial terms or using the distributive property most likely. And then addition and subtraction is all about combining like terms. And then we're going to find compositions of functions. This is when the book gives us two functions and it asks us to plug one function into the other. Okay, so like function notation. Composition, once again, that's just plugging in a function into another function. Okay, so here we have our operations. So let f and g be two functions with intersecting domains for all x values in the intersection. The sum, the product, the difference, and the quotient of f and g are new functions defined as the following. So the sum, if it's presented to you as f plus g of x, that is corresponding to taking the entire function of f of x and then adding it to g of x. Once again, combining like terms when we're talking about sum or addition. We want to combine like terms. The difference, f minus g of x, is equivalent to f of x minus g of x. Okay, so once again, we're looking to combine like terms on addition and subtraction. These two here. The product, f times g of x, it's shown with just a dot, okay, using the multiplication symbol. And that's equivalent to taking the entire function of f of x times the entire function of g of x. We're going to use the distributive property a ton when we are multiplying. Okay, and then the quotient is f divided by g of x, which is equivalent to the entire function of f of x divided by g of x. And honestly, the quotient is probably the easiest one because it's a lot of just rewriting and simplifying. It's taking one function, putting it over another function, and then making sure it's in its simplest form. So like canceling out x values, stuff like that, but quotient's pretty simple, and it's the least labor intensive. All right, so first one. We are given f of x is equal to x squared minus 2x, g of x is equal to 3x minus 4, and h of x is equal to a negative 2x squared plus 1, and we want to find the function and the domain for f plus g of x. So f plus g of x, remember it's equivalent to the entire function, so f of x is x squared minus 2x. G of x is equal to 3x minus 4. And I'm just writing them down right now. Like I said, it's going to be very algebraic intensive. So what I have here, f plus g of x, this is my f of x equation, or function right there. This is my g of x function right there. It's addition, so I don't have to, I'm going to just treat this as I'm combining like terms all the way across. So looking at it, x squared, there's no other variable to the second power. So x squared has to stay. Okay, negative 2x plus a positive 3x is going to give me a positive 1x or x. So that's taking care of x squared. That's taking care of my 2x values. And then negative 4 as the constant. That stays. Okay, so here is where it's very helpful to know what type of equation this is. Okay, this is one that we've worked in both Algebra 2 and early stages of pre-calc. It's what's known as the quadratic. The quadratic equation has a domain of all real numbers. This fits the form of the quadratic with ax squared plus bx plus c. So this domain is from a negative infinity to a positive infinity, or all real numbers, however you want to put it. But interval notation makes it nice and quick. Once again, this was addition, so we're just thinking about combining like terms. So the definition, again, that just tells you that we're going to take all of f of x and we're going to add it to all of g of x. There they plug in their two functions. There they simplify them. okay, by combining like terms. The domain of f and g are both negative infinity to positive infinity, so the domain of f plus g of x is equal to a negative infinity and to a positive infinity for all real numbers. Okay, on to the next one. We're given the same equations. Okay, f of x is still equivalent to x squared minus 2x. G of x is still 3x minus 4. And h of x is a negative 2x squared plus 1. And they're asking us to find what f of h of x is. So x squared minus 2x minus 2x squared. Okay, so we did our addition problem. Now it's time to do our subtraction problem. Once again, they're handled the same way. The one thing that changes a little bit with this is it makes it much easier if we distribute this negative. Okay, if we distribute a negative in front. What that does is it changes our subtraction sign between the two quantities to an addition sign, and it changes the sign of each of these. So to distribute the negative, turn my subtraction to addition, and then I adjust the signs of each of the negatives. So it was minus a negative 2x squared. Well, that's equivalent to adding a positive 2x squared. And then it had plus 1, but we were subtracting, so subtracting a positive 1, that's equivalent to adding a negative 1. Okay, that's called distributing the negative. And all it does is it allows me to add these, okay, and it makes it a little bit easier to keep track of my signs as they're going. So once again, I'm going to combine like terms. I have x squared and a positive 2x squared. We're adding them together, so I adjust my coefficient to make 3x squared. Okay, so that's taking care of those. That's taking care of those. I have no other single x value, so my minus 2x must stay. And I have no other constant, so I can write it as plus a negative 1 or subtracted to 1. So these are the exact same. They're equivalent. It's just however you want to put it. So 3x squared minus 2x plus a negative 1, or 3x squared minus 2x minus 1. All right, answers. And then once again, we got to answer what's the domain. So this, once again, is a quadratic. Okay, and the quadratic has a domain of negative infinity to a positive infinity. So we define the two functions. Okay, they plugged them in. Then they carried out their subtraction. Okay, so 3x squared minus 2x minus 1, or 3x squared minus 2x plus a negative 1. Like I said, I only distribute the negative because it makes my life easy. Okay, then I don't have to worry about, oh, I'm subtracting a negative number, which in all reality is adding. I'm subtracting a positive number, which is true subtraction. If I just distribute that negative through, it makes my life easy, and then I can just add. I can just add them back together. Okay, which pretty sure you guys, it was like in 8th grade math, when you'd have 3 minus a negative 4, they would tell you to change it to an addition sign and change the sign. So 3 minus a negative 4 is equal to 7. So it's the same principle, just allows you to keep track of your negatives. Since the domain of both of our quadratics is from a negative infinity to a positive infinity, the domain of f minus h is equal to the same or all real numbers. Okay, multiplication. So we're given the same functions once again. Okay, we're given x squared minus 2x for f of x, g of x is 3x minus 4, and h of x is negative 2x squared plus 1, and they want us to multiply f and g of x. So we have x squared minus 2x times 3x minus 4. Okay, these are two binomial terms. So in this case, we are able to use FOIL, okay, where we take our first terms, multiply them, our outside terms, multiply them, our inside terms, multiply them, and our last terms, multiply them. If you really want to break it down to what FOIL is, it's the distributive property twice. We have to take this x squared times both this 3x and this negative 4. Okay, those are your first and outside terms. Then we have to take this 2x times both this 3x and this minus 4. Okay, those are your inside and last terms. Take everything. So if there was a trinomial out here, there was a negative 1 associated. We would have to distribute 3 times. Okay, and it turns into a lengthy process. Okay, but since it's binomial, we can just treat it like FOIL. X squared times 3x gives me 3x cubed. X squared times a negative 4 is negative 4x squared. Okay. Then negative 2x times 3x, that gives me a negative x squared. And then negative 2x times a negative 4 gives me a positive 8x. And one little cheat that I do, okay, you notice I didn't write them all horizontally. Okay, with the multiplication, the first term multiplied by the second term, that's going to give us our highest exponent. Okay, 2x squared, that gives us our x squared times negative 4, that gives us our x squared. Negative 2x and a positive 3x, that equals 6x squared. I just lined them up. And then I'm going to add them together. That way, I'm keeping my exponents straight. That way I know, hey, what to combine with what. So 3x cubed had nothing to combine with it, so 3x cubed. Negative 4x squared plus a negative 6x squared, the negative 10x squared, plus 8x. Okay, once again, this is a polynomial. Polynomial functions have a domain of all real numbers. So my domain is from negative infinity to positive infinity on my answer. And my answer function is 3x cubed minus 10x squared plus 8x. You could also use the domain for a cubic function that we covered in transformations. Same exact thing. To help you with the domain of the function. Bang. Okay, once again, they set it all apart. And then, like I said, the distributive property. If we have 3 terms in the first, multiplied by 3 terms in the second, we have to bring each and every single one of those across. Okay, in the domain, it's a cubic function, so we know the domain is from negative infinity to a positive infinity. And we learned that in section 1.5. Okay, here is your division. So we want to find h divided by f of x. Okay, so understand that that's equivalent to h of x divided by f of x, which is equal to negative 2x squared plus 1 divided by x squared minus 2x there. And then we don't want to simplify it too much. Okay, we could, but we really want to look at the domain. So like I said, when it comes to the quotient, it's a lot of just rewriting. So if this is an equivalent function, it would work. More or less, it's taking h of x and putting it over top of f of x. Okay, that's from the definition. Then we just plug them in. And then once we talk about the domain, okay, once you're dealing with the domain, it cannot be whatever makes this 0. Okay, it can't be that. So it looks like, and we could graph this and we'd be able to see it in Desmos. So 0 squared minus 2 times 0 is 0, so that's going to make it undefined. So x cannot equal 0, but then 2 squared minus 2 times 2, that also makes it 0. So x cannot equal 0 or 2. And if you're ever in doubt when it comes to the domain of these equations, feel free to plug it into Desmos. Okay, Desmos, because you'll be able to identify. So we have negative 2 squared plus 1 quantity divided by quantity of x squared minus 2x. Okay, and if you're looking at my graph here, you can see that 0 is undefined. Okay, my graph approaches 0, but it never really touches 0. Then I have this little sliver, which fills in the area that's greater than 0, but less than 2. So I have 2 infinite discontinuities here. I have an infinite discontinuity at 0. I have an infinite discontinuity at 2. Okay. It won't even let me show it. I'd have to click on it. Okay, there's a bigger version of it. So we could express the domain as x can equal 0 or 2. Or we could go using interval notation from a negative infinity, 0. This one's going to have 3. So interval notation saying the exact same thing. Negative infinity to 0 with parentheses. Then we would have a parenthesis with a union between 0 and 2. The union of 2 to a positive infinity. Or in other words, x can equal 0 or x can equal 2. Okay. Looks good. Minimize that, share my screen, click it or tick it. Okay, defining the quotient of 2 functions. There they go, they plug it in. That's what we're going to be left with. The domains of f, h, and f are both negative infinity to positive infinity, but x at 0 or x at 2 yields a 0 in the denominator. Okay, so that makes it undefined. That gives us our infinite discontinuity of our new function, right? Of our new function, what we graphed on Desmos. And you can see the domain from negative infinity to 0 with a union from 0 to 2 with a union from 2 to positive infinity. Or in other words, x can equal 0, x can equal positive 2. Okay, and that's simply because when we plug in 0 and we plug in 2, it makes the graph of f of x equal 0. okay, which causes us to have an undefined function. Okay, so I've done the algebraic steps. Now we're going to walk through the slides. So we're finding f plus g of x, f minus g of x, f times g of x, and f divided by g of x for each when f of x is equal to x squared plus x, and g of x is equal to x minus 3. Okay, I'm not going to do these algebraically because I want to give you guys a little bit of time to work through it, and I think the slides do a good job. Oh, never mind. Multiple choice question. Don't got time to go over it. Okay. Composition of functions. Law. Okay. So composition is when we're actually going to plug in a function into the variable of another function. Okay, so if you look, it has f and then this open circle of g of x. Okay, so what that is equivalent to is f of g of x. So g of x is where we're going to plug in everything. So the domain of f of g of x includes all x values in the domain of g that map to g of x values in the domain of g as shown. So f has the domain, g of x. So in other words, we are plugging g into f of x for the variable. Okay. So we're given f of x, which is equal to 2x squared. G of x is equal to x plus 3. Okay, and we want to find what f of g of x is. So f of g is equal to. All right, here we go. So we're here. First step, let's write out f of x because that's what we're going to plug in. Okay, since we have f of g of x, we have one variable. This equation of x plus 3, which is for g of x, has to be plugged into each variable every time it occurs. So in all reality, f of g of x is equivalent to 2 times x plus 3, which is squared, minus 1. So here, we got to use order of operations. We cannot distribute this 2 in first. We have to FOIL this. So for this portion, x plus 3 squared, it's x plus 3 times x plus 3. We would FOIL that to have x squared plus 3x plus 3x plus 9. Simplifies down to x squared plus 6x plus 9. But then we have to multiply everything by 2 because of that 2. We have to distribute, and our constant would stay. So I'm running out of room. I'm going to bring it top right. 2 times x squared gives me 2x squared. 2 times a positive 6x gives me a positive 12x. 2 times a positive 9 gives me a positive 18. And then I'm going to subtract 1. So my final answer is 2x squared plus 12x plus 17. Okay, and the key thing is we want to use order of operations. So I wrote it out. I plugged in g of x into f of x for each occurrence that x happens. This one, we're fortunate, only had 1. It was squared, so I had to FOIL it first to get x squared plus 6x plus 9. And then I had to distribute my 2 in. That's what gave me 2x squared plus 12x plus 18. And then my constant of minus 1 always stayed. So that reduces the constant of our new polynomial. Like I said, not terribly difficult, just a lot of work. Just a lot of work. So plugging in f of x plus 3. So we substitute it in, and this happens for each and every x variable. Okay, if there was more than one, we would have done it more than once. We have to square, so we had to FOIL first. That's how they got x squared plus 6x plus 9. And then they distribute the 2 in. Okay, they distribute the 2 in first before they subtract. PEMDAS. Parentheses, exponents, multiplication, division from left to right, addition and subtraction from left to right. Okay, huge order of operations here. So we're given our answer and we got it correct. Okay, this one, pretty simple. We're given f of x, which is equal to 2x squared minus 1, and g of x, which is equal to x plus 3. Now, instead of plugging g of x into f of x, we're going to plug f of x into g of x. So first step, let's get an idea. So it's g of 2x squared minus 1. We're going to plug that into our x value. Okay, here it's nice and simple because we don't have an x pointer. We don't have to FOIL it all out. We don't have to do the distributive property. At this point, we have to combine like terms, right? Because it's x plus 3. Our x value is now 2x squared minus 1 plus 3. The only thing we can do there is combine our two constants of -1 and a positive 3, and we will be yielded 2x squared plus 2. And that is our answer. So you can see it's plugging it in and carrying out order of operations. Okay. So I have the first one. I need to copy down the second one. Give me 1 second. It was 2x squared. So this was f of g of x is equal to that. And then g f of x, which is equal to 2x squared plus 2. Okay, this is kind of the follow-up question. So what it's going to ask us to do is, now that we have, okay, we found what f of g is. Okay, f of g was 2x squared plus 12x plus 17. They want us to find out what f of g of 2 is. Okay, so what we can do, basically what it says is to evaluate the expression you wrote in part A. So in other words, we had the answer of 2x squared plus 12x plus 17. Now they just want us to plug in 2 for our values and evaluate it that way. Okay, so here's f of g of x. And we want to find f of g of 2. So f g 2. So that's equal to 2 times the quantity of 2 squared plus 12 times 2 plus 17. Once again, order of operations, 2 squared is 4 times 2 is 8. Plus 12 times 2 is 24. Plus 17. So 8 plus 24 is 32. Plus 17 is 49. So f of g of 2 is equal to 49. Ta-da! Watch, I'm going to click on the slides. I did it completely wrong, but it'll be okay. We're smart kids. We can figure it out. Awesome. Didn't show a lot of work. Once again, that's just plugging it in. Okay? So the key thing is we had to find what f of g was first, and then we had to plug 2 in. Why did it do that? Okay, multiplication question. Okay, finding a composite with a restricted domain. Okay, so they want us to find f of g of x. So f of x is equal to the square root of x minus 1, and g of x is equal to x minus 1 squared. Okay, this will be the last one that we go over. Okay, to find f of g, you must first be able to find g of x, which is equal to x minus 1 squared, which can be done for all real numbers because it is a polynomial or a quadratic. Okay, and they're all talking about domain here. Then you must be able to evaluate f of x, which is equal to the square root of x minus 1 for each of these gx values. It's going to only be done when g of x is equal to greater than 1. That's because we can't take the square root of a negative number. So when we plug 1 in there, we get the square root of 0, which is 0. But if we were to plug 0.5 in there, it'd be the square root of a negative 0.5. And even though I know we could do it with imaginary units, we can't really do it because we were working in all real numbers right now. So excluding the domain from those values for which 0 is less, namely when 0 is, when x is between 0 and 1, the domain of f of g is therefore a negative infinity to 0 with a union from 2 to a positive infinity. And you'll see the graph once it comes up. So f of g of x squared minus 1. So they plugged it in. They expanded it. Okay. So x minus 1. They FOILed that out to get x squared minus 2x plus 1 minus 1. Or x squared minus 2x. Okay. And then this second part, more or less what it comes down to when it's restricted domains, after you do the carrying out, similar to the way that we did with the composition of functions, to answer these questions is very easy if we graph it. So we have the square root of x squared minus 2x. So everything that they've done to this point is just plugging in. Square root of x squared minus 2x. Square root x squared minus 2. Okay, so from here to here, all of these x values are imaginary numbers. Okay, you can see it picks up at 0 because 0 squared minus 2 times 0 is going to be the square root of 0, so we'll still get 0. But if we were to plug in 1, we'd get 1 squared minus 2 times 1, which would give you a negative 1, imaginary number. So anything that makes x squared minus 2x negative is not a part of our domain because we have the square root function. Okay, it's not terribly difficult. I don't like the way the slides did it. They asked you to identify the domain first, which it's so much easier if we carry out, if we just do the function composition first, okay, and then carry, and then try to find domain. Okay, I don't understand why they would. You can do it that way, but it makes it much more difficult, in my opinion. I struggle being able to picture it that way. I'd much rather be able to do my equation first before I consider the domain. And that's because when I'm looking at domains, I can get a good sense about what's going on. But for me, the real key is I got to graph it, right? And there's no shame in that. I'm very visual. All right. So that's where I'm going to stop you. And that's where I'm going to stop lecture.